This question gives us an ellipse defined parametrically, x equals 5 cosine t, y equals 7 sine t. So a particle is moving in an elliptical path, and at certain times we can figure out where it is, both x, like its x and its y coordinate at certain times using this parametric equation. So determine the point on the curve at 2 pi over 3. So that means we're just going to plug into our parametric equations to find out where it is. So where is it after 2 pi over 3 seconds? Well, it's at 5 cosine of 2 pi over 3. And then it's at 7 sine 2 pi over 3. So we're in our second quadrant in 2 pi over 3. So cosine is going to be negative, and it's going to be 1/2, so we get negative 5/2. And then sine is going to be positive, and it's going to be root 3 over 2, so we get 7 root 3 over 2. So our point is negative 5/2, 7 root 3 over 2. Now what part B is saying is what is the slope of the curve at 5 pi over 4? So this is different. It's not saying where is the particle, it's saying what is the slope of its path. So for this one, we're going to have to find our derivative and then use that to find our slope. So again, we have x equals 5 cosine t and y equals 7 sine t. So then dx dt is negative 5 sine t, and dy dt is 7 cosine t. And why are we finding that? Well, eventually we want to be able to find dy dx because that's our slope. So what we can do is find out what dx dt and dy dt are at 5 pi over 4 and then use that to figure out our slope. So dy dt is 7 cosine 5 pi over 4. That is our third quadrant where cosine is negative and it's equal to root 2 over 2. So we get negative 7 root 2 over 2. What about y? We have negative 5 sine of 5 pi over 4. Okay, again, third quadrant, sine is negative. It's equal to root 2 over 2, so it's negative root 2 over 2 times negative 5 is going to be positive 5 root 2 over 2. Okay, so then all we need to do is do dy divided by dx. And because they both have a root 2 over 2, those are going to end up canceling, which is going to be nice. So dy dx equals, our dy was negative 7 root 2 divided by 2, and our dx was 5 root 2 over 2. So then the root 2 over 2's cancel, just leaving us with negative 7/5. That's the slope of our elliptical path at t equals 5 pi over 4. And then finally, part C says convert this to Cartesian form. So we have x equals 5 cosine t, again, and y is 7 sine t. And we need to use the fact that sine squared plus cosine squared equals 1. Okay, because if we can do that, we can get cosine and sine into the same equation, and hopefully that'll help us convert this to Cartesian. So first, we notice that it's not cosine plus sine, it's cosine squared plus sine squared. So we need to square these things to get a cosine squared and a sine squared. So we have x squared is 25 cosine squared. Y squared is 49 sine squared. Okay, so then again, we don't have 25, 49 in our equation over here. We only have these, so we need to isolate them. So we get that x squared over 25 equals cosine squared, and y squared over 49 equals sine squared. So now we have it. We have cosine squared, we have sine squared. We can just add them together and get 1. So we have y squared over 49, that's sine squared, plus x squared over 25, that's cosine squared, and that's equal to 1. We have x's, we have y's, we have it all in one equation, so this is our Cartesian form of that parametric equation we started with.